everyone, this video is going to be on the 3 gas laws or relationships that we discussed in class that relate temperature and volume, pressure and volume, and temperature and pressure. All 3 of these relationships do have formal names. You are not required to know them. What I do want you to understand is what the relationship is, what it looks like when we graph it, why it is that way, thinking about the behavior of gas particles, and then just sort of link it in your mind to some sort of phenomenon that you've seen that's going to help you remember that relationship. So I'm going to start off looking at temperature and volume. It's the first one we looked at in class, and what we found was that as temperature increases, so does volume, right? And opposite, as temperature decreases, volume decreases. We had an equation that helped us predict exactly how much either of those variables might change, and that was, V1 over T1 equals V2 over T2. If we graph that relationship, I know that if I increase temperature, volume on the other axis should also increase. So I start low, and high, and high. That shows me that this is a direct relationship. When one goes up, so does the other. If I backtrack and move one down, the other variable also goes down. And if we stop and think on a particle level, what's actually happening here? When we increase temperature, you guys know that means I'm increasing the kinetic energy of the molecules. Those molecules are moving around faster and faster. So you can say that faster moving molecules push out the walls of the container. And that's if our container is flexible, right? If we're in some sort of rigid cylinder, this isn't going to be able to happen. Volume won't be able to change. But if you're in something like a balloon, those gas particles are able to push on the outer walls of that balloon and make it bigger if temperature is increasing, or they can start slowing down and the volume can decrease as they push less frequently on those walls. So I've always found thinking of balloons to be the easiest thing about this. In class, some of you took a water bottle and stuck a balloon on the top of it. Well, that's a terrible balloon, but you get my drift, right? Balloon has a little bit of air in there. As soon as you dunked this into some hot water, right, added some heat, that balloon was able to expand because those gas particles were moving faster and required more space. Increase in volume due to an increase in temperature. That's known as Charles's law, but again, this is what I want you thinking about when you think volume and temperature. If you look towards pressure and volume, it's a little bit more interesting because as we increase pressure, increase pushing force, our volume is going to decrease, or vice versa. As pressure decreases, volume increases. The mathematical relationship we wrote for that was that P1 V1 is equal to P2 V2. This relationship is an inverse relationship. When something goes up, like pressure, my volume isn't going to increase. Instead, it's going to decrease. And often you're going to see that represented with a curved rather than a straight line. All we're showing is that as pressure increases, volume actually decreases as a result of that change. On a particle level, this makes sense. If we push harder on the outside of our container, molecules are forced closer together. Pushing harder forces molecules closer together. Kind of on the opposite end of the spectrum, if we force the molecules closer together ourselves, those molecules are going to push harder and harder on the container that we're shrinking on them, right? So either way, when molecules get closer together, we get more collisions. And it's really this idea of collisions that results in our conclusions about pressure. So in class, I think one of the easiest ways to visualize this relationship is to remember the little PVC potato gun that we tried out, where if I take a tube of PVC and clog the two ends with potatoes, and then I push this potato in, what I'm going to do is decrease the volume of gas trapped inside, building up the pressure until the pressure builds up enough that this little potato wedge just shoots right on out. So as I decreased the volume, the pressure inside the tube increased, showing that inverse relationship. And again, that's just a result of these molecules of gas having more and more collisions with the walls of the container and with this potato plug at the end. If we look at our third relationship between temperature and pressure, we're going to see something very similar to what we saw with temperature and volume, that as we increase the temperature, pressure also increases. And in sort of opposite terms, as temperature decreases, pressure also decreases. Because this relationship is another direct relationship, the equation looks very similar. P1 over T1 equals P2 over T2. Again, because it's a direct relationship, as one variable goes up, so does the other, looking exactly the same as our temperature volume graph did. On a particle level, again, if we think about pressure in terms of collisions, this relationship makes sense. Faster moving molecules collide more with their container. What that tells me is if I heat up these molecules, they're going to move faster, the temperature is going to increase, and they're going to hit the sides of the container more and more and more, increasing the pressure because our volume isn't changing. They can't push back on those walls of the container and just increase the volume. If we're keeping volume consistent, we're going to be increasing the pressure. And there's lots of ways you can think about this one. Oftentimes, I just like to think about it in terms of a can of hairspray. There's my hairspray can, right? If I heat up a can of hairspray, this is a very rigid container. The volume's not going to change. If I heat this thing up enough, all those molecules inside that can of hairspray are going to start moving faster and faster and faster until the pressure inside here builds so much that our hairspray can is just going to rupture. So however it is you think about it, however it is you remember it, these are the three relationships I want you thinking about. And I really want you thinking in on the particle level explanations, because that's what really builds your intuitive understanding of these gas relationships. Now, if you're feeling a little bit less intuitive, of course, there is a shortcut. So if I slide back to the top of my paper and I write a P, T, V across the top line for pressure, temperature, and volume. One thing that I can do just to kind of cheat and make sure I'm remembering these relationships correctly is cover up the variable we're not interested. So let's say in this column, we didn't really talk about pressure here. We assumed it remained constant. So I'll cover up the P, leaving me temperature and volume. If I'm going to make a change to either one of these, I can either move it up to show an increase or down to show a decrease. So let's say I decrease temperature. I move it down. If you notice, volume started up here, volume is also decreasing. Let's say I increase the volume. I move it up. Notice the T is now moving up off the screen. As volume increases, temperature is increasing, right? What about here? Pressure and volume. I can cover up my T. If I decrease the pressure by moving it down, that V moves up off the screen. As pressure decreases, volume increases. Lastly, if I cover up my V to take a look at this pressure and temperature relationship, we'll see it's another direct thing. As I increase the temperature, that P also moves up off the screen, showing me that when temperature increases, pressure increases. So feel free to use this trick, write it on the top of your tests, write it on your homework, whatever the case may be. But keep these three relationships in mind because we're going to use them when we work to combine them all together into one big combined gas law.